Okay, so thank you, Chris. So now, so we talked about hardware, how great it is, resiliency, performance, and all those things. But without the key software features that are required to provide the high availability and the data services that a primary data center deployments demand, this probably is not going to be expanding the way Steve highlighted earlier from tier 0 to tier 1 and so forth. So this is exactly what we are going to talk about in this section, and we will go through at a very high level for set the context as to what the software stack looks like. And then, since this is a very technical audience, we had put together a special focus on doing the theory of operation, the data, how does that I/O travel as it traverses through the different stack, to highlight how we have optimized and integrated with our software. We'll have we have some slides on data services also, because these are the key to enable the deployment into the primary data centers. So we have high benchmark being established by the existing players, and the flash arrays with the software features have to match up to that before being acceptable as a VMAX or other replacements. So very quickly, this is a very simplified Concerto software stack. This, if you go down under, we have our Violin optimized backend drivers, depending on 7300 or 7700 deployment. It goes ahead and picks up one of the drivers. But as you move up, this is where the LUN services come in. Thick LUN, thin LUN, and the dedupe LUN. We are probably one of the few vendors who can provide you with the choice of having thick and thin and dedupe all coexisting in the same box, and also online transforming the dedupe LUN into the thick LUN or the thin LUN, based on what you discover after you have deployed your application, whether they're benefiting from the deduplication or not. And on top of that is all the data services, and we're going to go take a deeper dive into the as the IOs go into the deep what happens to the IOs when they go into the thick or dedupe LUNs. Okay. So on top of these LUN services, now you have the data services, and these are the critical part for being to enable the deployment of arrays into the data center. So we have CDPs, replication, sync mirroring, snap, stretch metro cluster, and host of that. Not able to fit it in over here. And then on top, you have the most popular the SAN protocol driver. So this is what goes into the 7300 controllers. In these ones, this entire software stack goes in over here. Then to complement this, we also have the host side software agents to help us with the driving application consistent snapshots. And we have it available for both the virtual servers as well as the physical servers. Any questions on this? Okay. And this is, I'm not going to go into the details of this. I had hoped we'll have more time, but this tells you the kind of the software portfolio that we have built up, intimately optimized for our flash platform. Yeah.
Where is the analytics part?
So we have manageability, call home, and so this is where the analysis sort of happens at the higher level, and then the analytics, two different levels of analytics. What we see from the data and the management software, and then the deeper analytics of what's going on into the VCM VIM to determine the reliability of the VIMs and all. That's part of the platform software, which Pat will be covering very soon.
Okay, but do you have some kind of cloud-based analytics? That the customer can compare his system with others?
Yes, so we have Symphony software coming up. So when we go into the Symphony software, we'll cover that, what's available to the customer, and what we analyze at call home, and how we propagate it back to the customer. That is coming up as part of the Symphony software. Excellent questions. Yeah.
You've got mobile devices noted up there in the top left. Is that are you running that on HTML5 for your interface, or what?
Andrew, HTML5.
For your dedupe store, since you're illustrating two different hash caches, is one in memory, one on disk, or how's that being handled?
Very good. And this is where Tim is going to cover, but yes, we use a combination. We have things in the DRAM on the controller, and then things into the DRAMs on the VIM. So again, no UPS and no SSDs. This is what our motto is. Okay. So there are three broader categories of the software: the Concerto, the data management software that sits into the controller, and management services. This is the data path services, and the deduplication services. This is client-server model, so it scales. As in future, as we want to go into the multi-controller node, we'll have a deduplication running in all 4, 5, or 6 controller that we choose to, and then host software stack. I know I rushed it, but I wanted to give now time to Tim to walk you through the data path of the thick LUN, dedupe LUN, and hopefully you'll answer the questions that you have. Okay.
So now you can ask. Next couple slides, then maybe ask me questions. Okay. Hi, I'm Tim, a resident Bearded Australian. Hope you can get my accent. So first of all, I want to just deal with the thick and bearded Australians, right? They're everywhere. Got to watch them, right? So first, I just want to go through the thick and thin data path, right? So the important thing that we're trying to illustrate here is that this is a fully scalable multi-core architecture, highly optimized for the Flash engine that we've got underneath us, as you've heard all about. Now, these hardware guys, they do a great job, and they give us software guys this super fast hardware that we have to then feed properly, right? And that's the hard job that this has to do. So as you can see here, this scales with core count. We have these fully independent queues going down for each particular CPU. As Intel comes to the party, they're always giving you more cores, faster cores. Well, this is how it scales, okay? There is zero contention in this thick and thin data path.
Scale out, right?
So just yell out for questions as I'm deaf as opposed. Right. This is highly optimized for the Flash engine underneath us, right? There's no buffer copying. Jim was talking before about how we can have so many IOs in flight at one instant, like 60 IOs at least in flight at one instant to get that good parallel performance. This is designed to support that, right? We have to push those IOs down as fast as we can with as high amount of concurrency as we can. Same is true of any system, it's just this system goes so much faster that we really have to worry about it. There is no SCSI in this, it's too slow. We get it right out of the way, we go directly over that PCIe link that we were talking about before. Then it hits the V-Rate engine, and then that parallelizes it further underneath. We take application hints, so this is the likes of your SCSI unmap, ATA trim, that kind of thing, hot and cold data separation. We can take hints from that. As Chris was talking about at the Vim level, we can also pass that through the software from our level. Otherwise, there's the danger that could get in the way, and we don't have that. There is zero read and write amplification at this level in the thick and thin path, right? So customer writes 4K, 4K gets all the way through this path. No metadata, no amplification. This is not new. This is mature and baked. We spent a long time making this work, and we're making this work properly in all cases across lots of. It took a long time, but across all the different platforms that we have, and the different platform generations that we have.
So does it support something like vVols and VASA and
Yes, and I'll just punt that to Gominda, who's going to talk about that high-level stack that sits on top.
Yes, we do support VASA, VAI, vVol is in progress. Just a quick answer, because I know whether we'll have time towards the end or not. Yeah.
Okay. And it's a layered architecture, and thick and thin provides, roughly speaking, the bottom layer of this, the core software data path. We'll talk more about that next. Okay, so as you can see over there on the left, we have thick and thin VDEVs. We've got the target drivers up the top and the flash basically down the bottom. We have this abstraction here, which we call downstream, such that on the 7700, that scale-out platform, the software stack looks the same. Right? We just unplug the PCIe flash driver from the bottom and plug it into the scale-out storage driver. But most interesting for me, because this is what I do here, is we talk about dedupe. We can see dedupe is a parallel LUN service, parallel to thick and thin. I won't dwell on this. The next slide will drill into it some more, but we can see that they pass through data services first. All your snapshots, CDP, replication, sync mirroring, all of that is up the top. Thick, thin, dedupe, doesn't matter. You still get all of those services. They can intermix and even switch between, as we talked about before.
So
now,
switching between, how would that be handled from a thick to a dedupe?
From a thick to a dedupe? Mm-hmm. Do you want to handle this
so
one?
so that is a decision point you have to make. Yeah. So today, if you are switching between the dedupe to thick or then, that those are the snapshots that we'll have to recreate, because a different kind of snapshot in that case will get created.
Okay.
Yeah.
So will it, if we went thick to dedupe, will it go through, analyze the data in a post-process fashion, and do that cleanup?
Yes. Yes. So from the user's point of view, nothing has changed. They're continuing to use the data
Fully
in
online.
the background. It is transforming it.
Okay.
Yeah.
Yeah, fully online. So we actually use some of the data services on the top to make sure that's totally transparent. They don't even know that the LUN has changed. WWNs and all that, all the same. Okay, so just to...
Can I run a thick LUN and dedupe the snapshots?
Sorry?
Can I run a thick LUN and dedupe the snapshots?
Dedupe the snap. So thick LUN, you have a different snapshot policy. Dedupe has a different snapshot policy, but you can have snapshot across all the different kinds of LUN at the same time.
Right, but I'm going to create a thick LUN because I'm paranoid that any of your other data services are going to cause me some performance problems. But since the snapshots are just insurance, I don't care about their performance, and I want them to be efficient. Can I do that?
Oh, that's a good feature request. that have the snapshot of thick LUN go into the deduplicates. And I think so. There is a trade-off also, right? The snapshot inherently delay your performance and increase the latency, right? And if you add now the deduplication path also into that one, that will further add to the latency.
Well, when I access the snapshot,
right?
Assuming your metadata,
And all those,
structured that way.
Okay. Yeah, so no, so there's a good feature request that when you have the dedupe LUN, can I have the snapshot into the dedupe pool? We can look into that.
Okay, and then the other thing that's missing from this essentially timeline is where do you act?
Okay, that is coming up.
Slide.
Very good question. Just coming up.
Okay.
Yeah, so this is the block kernel the stack layer, and then there is the data path just coming up.
Yeah, and just back on that snapshot answer there, snapshots being copy on write, generally they contain the old stuff, right, and they decay out. So it's generally not so much in there to dedupe anyway. So now to your timeline. Okay. Okay. So first thing is this is just the dedupe path, right? No thick and thin anymore. We're building on top of that to provide dedupe services. First thing happens is we stage this IOP in the system. Right? We have a fully inline dedupe engine that comes after this, but before this we're staging it. Now, before this happens, we've got our data services, snapshots and so on that we just talked about before. We're staging this in the system DRAM, so this is what's happening up in that memory gateway, which is obviously volatile. If we lost power at this point, we would lose the data, so we haven't acted this to the customer yet. Right? We also are writing it down to what I'm calling the buffer line.
You have a system-wide supercap, so it's
not for this DRAM. We don't bother with this DRAM, right? Because this DRAM, it's not RAID protected. I wouldn't feel comfortable even giving that to the customer and saying I acted, but I only stored it in one piece of DRAM. It's not good enough for me. What we
not
do
good
is
enough for me either. But yeah.
Right. So what we do also, we keep it there just for speed. We also write it to what I'm calling a buffer LUN here, but as you could appreciate from what you've just learned about all the VIMs and VCMs, it doesn't necessarily even have to touch the flash, right? It just has to pass through the RAID controller and hit that DRAM inside the VIMs where it's power protected, to your point. Okay? So from that point, which is super fast, then the client gets an ACK.
Okay, but you are ACKing before the hash table lookup.
Absolutely, you don't see any of that here yet. It's just, all we did was write it to the DRAM on the VIMs essentially, right? Just as in a normal thick LUN write. So they get super fast latency and super consistent latency as well, which is almost more important for me, okay? Also, if the customer's workload is particularly misaligned or sub-block or so on, this acts as a buffer to soak that up. Right? Generally, you get that with some workloads. Okay, this means that we don't have to ask the application to reconfigure so much to make sure that happens so that our performance remains good. It's good anyway. Okay, so now the next slide will follow off down the bottom where this arrow is going, what happens afterwards, which is what Howard's interested in. Okay? Please stop me, I'm trying to go quickly. Okay, so this is what's happening after that DRAM. We'll call it the flush path so we can give it a name. First thing that has to happen in any dedupe engine, we have to divide this thing into chunks. We have a data stream from the customer. They gave us potentially a large IOP, 256K IOP or something. We divide it into a small fixed size chunks. Then we'll hash it. Then we'll take that hash and we'll look it up in this totally in-memory lookup engine. Right? There is no flash IO up to this point. So there's no latency, there's even a low latency, there's no latency there, there's no flash writes, no flash reads. The lookup process will give us one of two answers. This is the heart of dedupe. It will tell us that the block is not there, and that's unique. I'll talk about that later. Or it will tell us that it is there, and also tells us where it is and other information about that thing. Okay? Now, if we've got a piece of data in our hand, and the system's telling us it's already got it and where it is, we say, okay, well, all I need to do is remember that pointer, and we're done. So that's what we call a stub. We update this mapping, and we're done to the customer. Okay? Of course, this mapping has to be persistent and protected. This is the customer's data, essentially. So we aggregate that with nearby ones, and we write it down through VRAID, like we just discussed, and it becomes protected. Any questions on this so far? I'm going real fast.
Just one very quick question. You mentioned that the writes are acknowledged when they hit the DRAM on the VIM, so they're battery protected.
It's not a battery, but power protected.
Power protected, sorry.
Yeah.
Well, it's not acknowledged on the DRAM, it's within the write buffer.
Right, so we have two copies of the data here, right?
Which has its own DRAM. Which is
VIMs have DRAM.
Yeah.
VIMs have DRAM, which is underneath this LUN. That's power protected. The MG, the memory gateway, the Intel CPU thing, has got DRAM as well. It's not power protected.
Right.
So but it's cheap for me to get to. It's right next to the CPU.
Okay, so you've got 2 copies of it anyway before you acknowledge it's just one's power protected and one's not.
Not only power protected, but VRAID protected as well. Okay, so if this whole MG went up in smoke and all its DRAM went and everything, that's fine. We'll just pull it back out of the RAID.
So any data we have acknowledged to the customer, we have to be utmost sure that it is it's completely protected. That's where the second copy is going to the VRAID.
Yeah.
It's not even the mirroring and the 2 SSDs. No, it's VRAID protected.
Yeah. So it's as protected as any other byte that you wrote through a thick line or anything else. Okay, so we just did this one. Now what we're going to do is we're going to fall off the bottom of this slide and follow the unique data path. What happens if it's unique? Okay, we come in at the top. We've done this lookup. He told us it was unique. Well, unique, not only are we going to do deduplication, we're going to do compression. So we're going to compress that small fixed size chunk, which is going to turn it into an even smaller, probably not so fixed size chunk. The compression's good at that. Okay, so then what we have to do is take those odd sized chunks and glue them together into bigger pieces so that we can write them down to the array in an efficient fashion. I'll call that aggregation. Okay, we aggregate that right up so that it's as friendly for Vim garbage collection, which Chris talked about before. We don't have to do any substripe writes, which you talked about before. We get improved locality for garbage collection. Everything's good. Compression is tuned for the balance of compression speed and decompression speed that we need. You know, the customer has a read-write ratio. You can't just do this once. Finally, once we've got this data aggregated, we can write it down to the data LUN, which again is a thick line, or thin provision line sitting on VRAID. So once it hits that, it's protected. Finally, then we're the same as the duplicate path. We need to update that stub pointer metadata, and once again, we're done.
So the data is deduped and compressed?
Correct. Correct. You'll see that on the duplicate data path, there's no compression, right? Because we've already compressed it the first time when he was unique. But when he was unique this time, we come through and compress him, squish the space down even more. Remember, we're using pretty small dedupe chunk size, which already means you're getting a really good dedupe ratio compared to a big one, big block size. But we compress
When you say aggregate, you're aggregating, I'll call it different LUN data into the same RAID stripe?
But what we have is a global, across the array, a global dedupe engine. So you can have as many deduplication LUNs as you would like. This is one dedupe pool. So this gives you better dedupe efficiency. So yeah, then by necessity, that means you could be aggregating LUNs, data from different LUNs.
And thick and thin LUNs do not go through data compression?
That's true, yes.
Can you do any encryption?
Can we do encryption? I'll punt that to the hardware guys because...
Yep. So this model doesn't have the encryption yet, but this is coming up. Certainly.
Okay. And there endeth the life of this customer's write IOP. Of course, if his IOP was bigger than a single dedupe chunk, then we go around this a few times in parallel, not in a loop, of course, for each of those individual chunks. Once they're all done, his write is completed.
Are you hashing at the 1K level or at the 4?
At the 4.
At the
4K level.
Okay.
That's right. Given that the application workload really dictates what the optimal size would be for your deduplication ratio, then most applications are bigger than 4K anyway. So choosing the lowest common denominator of 4K, which also happens to be your memory page size and so on, then it's about as good as you can get. Okay, to tie all this together, I'll just go through the read path, which cements those concepts. But honestly, you can see here, we go through, we receive this IOP from the client, we go through data services again, snapshots and CDP and so on. Assuming we actually have to do this read, which we may not. We'll look it up in this stub metadata, and we might not even find it there, meaning the customer's never written it before. This is thin provisioning working, right? As soon as we find nothing there, we just return nothing really fast. That's about as good a job as I can do. Given that I then have to read this data, this tells me where to go and get it. It doesn't tell me the hash of where to then look that hash up and find it. It just tells me exactly where it is. So I don't need a secondary hash lookup here to impact the performance there at all. It tells me exactly where to go and get it. I go and get it. I decompress it really fast and return it back to the customer. We're done. If that IOP was larger than a single dedupe chunk, of course, I need to read multiple of these. Probably only need to read the stub once because we have locality there. Probably only have to read the data once because we have locality there. Decompress a few chunks in parallel, and we're done. Okay. That's about it for me, I think, unless there are any questions.
Okay, so any questions for Tim?
So the hash lookup, is that optimized and stuff like that? I mean, how do you, where's the hash table?
Where? Okay, it is of course persisted, so I can't lose it, otherwise I'd get into trouble. So that's written down to the VIMs in the same way everything else is protected by VRAID. But the hash lookup, where's my slide here? This lookup here, this is totally in memory. So inside the DRAM on the Intel board, the MG, that's where the hash store is. Essentially a cached copy of that. The real one's down there on the flash, so we don't have to worry about losing it. But yeah, hopefully that answers your question. And of course, we don't need to do that at all on the read path. It's all on the write path. Thank you.
Yeah.
So
Thank you, Tim.
One point. So if the hash table is in the in that module, so the duplication is not global, or you have a global hash table that is replicated or synchronized with all the modules in the. I'm talking about the
7700. 7700.
Right.
Yeah, in the 7700, the dedupe happens in the external controllers.
Okay, so same process, but okay.
Yeah, actually, we have done, in fact, better. In the 7700, we have the concept of performance optimized shelf and the capacity optimized shelf. In the capacity optimized shelf, deduplication happens right there. So what is the advantage we get? Then you can have the performance aggregation across the capacity optimized shelf as well. Okay. All right. So since we have only 10 minutes, okay.
But each shelf is its own deduplication realm.
Yes. Yeah. Okay. So very quickly, we have only 10 minutes. I just got warned by Sonia, and we have platform software and we have demo. So we'll try to see what we can do. But I wanted to take just a quick moment. So when you think about the primary data storage, there are certain software attributes and the software features that you think about that a software array should have. CDP, replication, different modes. SRDF has been around for a long time, so asynchronous, synchronous, and all those things. Stretch metro cluster for 0 RPO, 0 RTO, so that you cannot have any tolerance to any downtime. So stretch cluster should be there.
So what distance?
Sorry?
What distance?
It should be there. Oh, no, I'm just listing it out. But we support, the stretch metro cluster, if that's what you're alluding to.
Yeah, how far?
Yeah, how far. We have tied it to the latency. As long as your latency is tolerable, and I have a table coming up, to around, to your workload, which is we don't recommend anything more than the latency of anything more than 10 millisecond or, 10 to 15 millisecond, we say it's not a good fit for the stretch metro cluster.
But to the point where your performance is going to be disk-like anyway.
Yeah, disk-like anyway.
10 is higher than I thought you'd accept.
Yeah,
Okay.
so it depends on the customer to customer, but typically dark fibers and all those things have lot lower latency, but that's where we try to guide the customer not to do that. But if they want to do it, as long as they understand the repercussion, we are fine. So you're right. So in the next few slides, I have just picked a few things that I wanted to showcase because I sort of anticipated we may run out of the time. So first, the replication. 2 modes, periodic and continuous. So periodic is more the snapshot based. You're capturing the changes and you're sending it across. And synchronous, this is important for some of the financial transactions where you want to maintain the write order fidelity. So every write that is coming in one order on the primary should go on to the secondary as well. So strictly maintain the write order fidelity. So those two.
For the point in time, what's the minimum granularity?
So we by default we have 15 minutes over there, but it's editable based on the customer's thing. But very good question. Typically, it should be done on the basis in connection with our field guys to determine your rate of change, your the pipe, the bandwidth it has, and then come up with a formula. So that's what. Hopefully, that answers your question. Okay. Policies, and then we also have policies for bandwidth optimization. You can set a throttling policy. Around this time I want to have only this much of bandwidth utilized and so forth, and encryption and all those things are there. So again, take away from this slide: replication 2 modes, periodic and continuous data replication. So this is a little bit of a deeper dive into how the periodic replication works. So I'm going to quickly browse through it. At the time the replication schedule is triggered, a snapshot happens on the primary side. On the secondary also, we take a snapshot to preserve the sanctity just in case the replication breaks down. The snapshot is taken. From the snap view, you read the differential data that has been accumulated and send that onto that side. If everything completes, that gets promoted as a replica. Otherwise, the snapshot is there to protect it from any kind of faults. So Continuous, you have a CDR journal where you're maintaining, because it is write by write. Every write has to be sent in exactly the same order that it has been received on the primary side. So we have a CDR journal, which is on the best case effort, asynchronously sending the data onto the target side, and just in case it is not able to catch up, we have a way so that it can fall back to the periodic replication. So full protection over there. Okay, now I want to spend a little bit of time.
I wouldn't call continuous data replication synchronous replication.
It's not synchronous. It's we are not using synchronous. This is asynchronous, but continuously, maintaining, thing. If you want the continuous, the synchronous, that's the next one. Okay. So now I want to take a pause here. So it doesn't matter what replication you have. There is always a finite number of RPO and RTO time involved. It's not zero RPO.
All three ways.
Sorry.
You're doing all three kinds of replication.
Yes.
Okay.
So it doesn't matter. So there is no RPO and RTO. And the reason I say there's two things. One is the RPO recovery point objective and the recovery time objective. Those two of them are really intimately tied to each other. One of them allows you to have every data, sacrosanct. Other one allows the continuity of the operation. And this is where our stretch metro cluster comes in. So in the 7700 model, if you take that, we'd allow you to have the setup stretched across two sites, so that if one site goes down, the second site takes over the personality of everything that the first site was offering transparently. So deployments like the SQL servers, which are capable of multi-site capable, we fit in really nicely. VMware, we fit in really nicely. So one site goes down, the second site is presenting the personality as if this site has never gone away. And we have put in tons of effort, for tiebreakers and all those things, and a lot of details to go in over there. But this is zero RPO, zero RTO.
And there's synchronous replication between the two sites?
Yes, synchronously done. This is synchronously. So this is where that 10 millisecond latency that was coming out, that every time an IO comes in, it has to get acknowledgement from both sides. So you need to keep it really small.
Okay, good.
And again, there is no external thing required. There's no external appliance required. You get it with our
So is the data actively writable from both sides?
Both the sides, yeah.
At the same time?
Yeah, but there is
so
a lot.
It's bidirectional synchronous replication.
Okay, so I'll clarify that. So there is active LAN on this side, and there is an active LAN on this side.
Yeah, but
so
they're different LANs.
They're different LANs.
Okay.
Yeah,
It's not multi-master replication. That shit's hard.
Would be.
Just checking.
Yeah, it's not. But this LAN can be simultaneously written from the host on this side and the host on this side, because it's a fiber channel setup. So they could both be coming, which is what the ESX servers do. They both could be coming to the same LAN from both the sides and writing to it.
So I multipath the server to both.
Go over there as well.
Yeah. Okay. So does if I'm accessing LUN A, does the storage system in location B forward those requests, or does the multipathing take care of it?
Oh, actually, we do even better. We transfer even the port IDs when the failover happens. Okay.
Well, you kind of have to.
We do that.
But while everything's running, I have a server in data center B writing to a LUN whose master is in data center A. Does that data path go through the storage system in data center B, or does the multipathing take care of it?
This is the multipathing, so you have to go over there. So there should be no, exactly that. For that reason, we wanted them to go straight away over there, so there's no extra hops involved. Perfect. So this is a stretch metro cluster. This is one of our showcase technology, and this has been enabling us to gain, some of the large deployments in over there, because now you can not only scale scale, tremendously, but you also provide a zero RPO and zero RTO, which is so critical for some mission critical appliance applications in the data center. Any questions on this?
Do you need anything like ADO bridges or any of that, or is it just controllers to controllers?
Yeah, so anything that is required from our side, we ship it. Any ISL switches and all those things. But there are certain requirements that the customers have to provide, the dark fiber and all those things. So that is for them. But other than that, the back-end fiber channel switches and all we provide. Okay, and this is again, this is unique to us, and this is all flash optimized. So we take care of all those transactions in a flash-friendly way.